Okay friend, welcome to my channel. So today I'm going to discuss about revision class of Raman Spectroscopy, and earlier I was discussed three spectroscopy like NMR, IR and UV visualized spectroscopy, which was based on basically organic chemistry. And now this is Raman Spectroscopy, which is based on physical chemistry. Okay, this topic is from physical chemistry. So now I am going to teach you Raman Spectroscopy. So before I start, so my request to please to all guys, if you are new in this channel, so please subscribe and like the channel and click the bell icon so that you can get easily notification and share with your friends. And okay, right, so Raman Spectroscopy. So this technique is also very useful for any branch like organic, inorganic, and this technique is basically also from this technique we get about the structures informations. Okay, and through this basically we deals the scattering of lights, not with its absorption. Okay, so basically we will discuss in this topic quantum theory of Raman scattering. Quantum theory of Raman spectroscopy. Sorry, scattering. Raman scattering. Okay. Right. So this is basically the as I told, this is also branch of spectroscopy, and here we deals the scattering of electrons. Okay, so here consider the photons of frequency mu, which is fall on the molecules. Okay, and if collision is elastic, then scattered photon will have to same energy as incident photon. Okay, and if however the collision is inelastic, means scattered photon will have to either higher energy or lower energy than of incident photon. Okay, then in that case the collision will be inelastic. Okay, so if we further assume that the total kinetic energy of the photons molecule remain unchanged before and after collision, then from law of conservation energy, h mu is equal to h mu plus E. This is before collision, and h mu dash plus E dash after collision. This energy will conserve, means there is no change before and after collision. And where you are already know about, this is the energy of incident photon, and this is energy of scattered photon. Scattered photon energy. This is incident photon energy, right? So and here E is the your energy of molecule, rotational, vibrational and electronic before collision, and this energy is after collision. Of the molecules. And if you rearrange this equation first, then we get the E dash minus E upon H is equal to mu minus mu dash. The simple rearrangement. If these things go this side and this energy go this side, so so here you can change like any way. This energy go this side, so E minus E dash minus E, and this goes this side, so H mu minus H mu dash. So you will get this equation. If you consider case number 1. If this energy, this frequency, mu, if this frequency is equal to mu dash, means before and after collision frequency is same, then what will happen? The energy will also will be same. So in this case the collision will be not elastic, the collision will be elastic. Elastic means we can say this case refer to the Rayleigh scattering. Refer to means we can say indicate Rayleigh scattering. Rayleigh scattering. Scattering. And second case, if this frequency is greater than less than your after collision frequency, then the case will be the so the energy here, if this greater than mu dash is here greater than mu, then whole things will be negative, and this whole thing will negative, then this will affect here also, so this will interchange. And if this is negative, then this will be negative, this will be positive, so energy here E is greater than E dash. So your incident energy of molecule is greater than after collision energy. Okay, so here we can say this case as a Raman scattering. Okay, Raman scattering. Raman scattering. Okay, right. Now case third. If this mu is greater than mu dash, then energy E dash is greater than E. Then this case is also we say the Raman scattering. Okay, but another name we will give here. If this incident energy is greater than after collision energy, then here we say the Stokes line. This will give from this case we'll get the Stokes lines. Okay, right. So basically here the scattered photon has here same energy as incident photon. Okay, in this case. So now we move to the structure, how to draw these things. If you see here, here this side is your energy. Okay, clearly seeing now. This side is your energy. Okay, and this is your ground state energy. This is another, this is higher expected energy. And if you are giving incident light H nu and it goes the higher excited state, and it will come back, okay, by releasing H mu energy. Okay, so H mu dash, sorry, this is releasing energy H mu dash. Okay, after collision, right? So here we can say this is the Stokes shift. This is from this process we get the Stokes lines. Okay, so you can correlate this process because you are providing H mu energy and you are getting this much energy, so lower than of incident energy. Okay, you see your here incident energy is higher than this, so your case here you will get case second. Okay, so in this case Stokes lines you will get. But another case, if you have this ground state, this is another first excited state. Okay, and this is higher excited state. So if you are excited here by giving energy H nu, okay, H nu photon energy, then you will get same amount of energy. Okay, H mu dash. Then we can say here Rayleigh. You will get Rayleigh lines. Okay, and last case, because here energy incident and after collision releasing energy both are same. Okay, so here the case is first. Okay, so this is elastic collision. This is this both cases are inelastic. In excited state energy. This is your, and this is mu 0 vibrational 0, mu vibrational 1 state. Okay, so if you are providing this much energy, okay, and you will get higher than of incident energy. Okay, so that means this case you will get third case, number third. Okay, so here you will get anti-Stokes line. Okay, right. So hopefully you guys understood what I am trying to explain. Now I will give some introduction about which scientist has first predict this by this method. Okay, so this Raman scattering has been predicted by the German physicist A. Schmeickel in 1923. Okay? It was observed by C.V. Raman and K.S. Krishnan in 1928. The Indian physicist C.V. Raman 1888 to 1970 won the Nobel Prize for Physics in 1930. Okay, for his work on the scattering of light and for discovery of Raman effect. Okay, this is the introduction type. I am not here writing because you should keep in your mind in future time. Anybody can ask question who develop and who got Nobel Prize on this field. Okay, so now I will discuss about the when a molecule goes to excited state, then the energy will be high and molecule feel unstable in vibrational state. Okay, so it return back to the original vibration area, means ground state. Then we can get the scattering line, say means relay scattering. Okay, if it is returns to the different vibrational state, this gives Raman scattering, means Stokes line. Here if you see, here it is returned to different vibrational state, means mu 1 vibrational state. Okay, so here we will get Stokes line. Okay, when the molecule initially in the first excited state, vibrational state. Okay, first here I am saying about the here, if the molecule in first excited state, vibrational state, and it promoted to the higher state, excited state, unstable, okay, vibrational state, and return to the ground state, this gain gives rise to Raman scattering, means into Stokes line. Okay, so you will get into Stokes lines. So whole this Raman spectrum of molecule consists Stokes and Stokes line situated symmetrical about the relay line, means these two are anti and Stokes line symmetrical situated about the relay lines. Okay, so this is the whole things. Okay, so now we move to the next thing. Next things is basically based on same things here. So here we this difference is called the shift, means mu minus mu dash is called the Raman shift. Okay, Raman shift frequency, a shift in frequency is called the Raman shift. Okay, right. So now move to the another things means I will give some notes, okay, which is very important. So this point, from this point examiner we can ask any question. Okay, so notes one. Now notes. So notes means here notes. As we know, the homonuclear diatomic molecules like hydrogen, nitrogen and oxygen, okay, which do not show higher spectra because they don't have any permanent dipole moments, okay, but they show Raman spectra since their vibrational is accompanied by the change in the polarity of the molecules. Okay, consequence of this change in the polarization therefore induce a dipole moment in vibrational frequency. Okay, so here basically this diatomic molecule H2N2O2 do not show IR, okay, IR spectra, but it show Raman spectra. Because I told you these molecules don't have permanent dipole moment, but it shows Raman spectra. Why? Because of by change the in polarizability of the molecule, because of change in polarizability of the molecules. Okay, right. Okay, so that means here change in the polarizability of the molecule means change in the induced dipole moment at the vibrational frequency. Okay, so that's why these molecules show Raman spectra. Okay, right. Now I will give you selection rule for this vibrational Raman spectrum for this diatomic molecule. So notes 1 to 2. So selection rules. Selection rule for vibrational Raman spectra of diatomic molecule is delta mu is equal to plus minus 1. So now right, so rotational Raman spectra of diatomic molecule. Now we'll discuss rotational. So you should keep in your mind the selection rule for this vibrational Raman spectra of diatomic molecule is del mu plus minus 1. Means change in vibrational energy difference is equal to plus 1 or minus 1. Okay, it should be, it may be plus or either plus or minus. Okay, minus 1. So now we will talking about rotational Raman spectra of a diatomic molecule. Okay, so here also you have to follow selection rule. So for pure rotational Raman spectra of diatomic molecule, so here is selection rule. For pure rotational diatomic molecule is delta J 0 either or plus minus 2, 0 and plus minus 2. Okay, so this is selection rule for rotational Raman spectra. Okay, so where J is the quantum numbers of lower rotational energy level, J is quantum number of lower rotational energy level. Okay, right. So now we discuss operative part. Operative part, rotational selection. Before solving related to this Raman spectra problem, you should keep in your mind this selection rules where you apply, because for vibration Raman spectra diatomic molecule is delta mu is plus minus 1. For this rotational Raman spectroscopy, selection rule is delta J is equal to 0 plus minus 2. And for operative condition, rotational selection rule is delta J is equal to plus 2. Okay, so last point, if delta J is equal to 0, then what it indicates? So it indicates correspond to Rayleigh scattering. Okay, Rayleigh scattering. Okay, this indicates Rayleigh scattering. Okay, and when delta J is equal to -2, then it indicate transition can ignore as a rotational quantum numbers of upper state must be greater than that of lower state. So okay, so you can ignore, okay, it, you can ignore it. So first resist, then I will tell you some other things. Talk about means energy level expression for rigid diatomic molecule. Okay, so by using selection rule of this above I written delta J is equal to +2. Okay, so now I am giving to expression, energy level expression of very very important. And so J is equal to J plus 1. So this is centimeter inverse. Okay, where J is 0, 1, 2, 3, etc. Right, and now we find the delta F J. So different of this J. Okay, means energy level difference. Now we find the for diatomic molecules. So this delta F J is equal to F J plus 2 F J. And if we put the value Fj plus 2, so if we see this expression, so how we will get Fj plus, so Fj plus 2 is equal to, you will get B and B J plus 2 J plus 3. Okay, you will get this expression, because if you see here you have only j, so you will get j plus 1. But if you have here j plus 2, so you will get here j plus 2, and here you will get 1 extra, so j plus 3 means j plus 2 already you have this level, and 1 extra added, so j plus 3 it become j plus 2. So you multiply this, so you will get j square and 3j and plus 2j and plus 2 into 3 6. Okay, so now you can easily 3 5j plus 6. Okay, so now this value you can put here, so you will get final delta f j is equal to b j square plus, sorry, you can multiply bj and b 5b j, okay, and 6b minus, you put fj value, this value, so I am directly putting here by after multiplying, so we will get b j square, okay, plus b. Okay, so sorry, minus, here you will get minus, here you will get minus b, because if you multiply here bj square plus bj. Okay, yeah, so your bj square bj square will cancel out, you will get here 5 bj and minus bj, so here you will subtract, so you will get 4 bj and plus this 6 bj. Okay, so finally you will get, you have to common here b, so then you get 4j 6. Okay, so delta f you will get this. Okay, so what this expression indicate, this is actually value in centimeter inverse. So okay, so here this expression has different applications. Okay, so application means here I am talking about the energy level diagram for rotational, okay, rotational spectra of these diatomic molecules. Okay, so according to this I am trying to draw rotational Raman spectra for this rigid diatomic molecules. Okay, right. So you have this in mid of this is actually indicate wave number. Okay, and you have this delta, earlier I told you delta j0 is equal to indicate relay. Okay, Raman relay. Okay, relay lines, and from this equation the each anti-Stokes line first how can we say first Stokes lines or first anti-Stokes lines appear at distance how much, 6b. Okay, so here you first Stokes, here you this side is anti-Stokes and this side is Stokes, so distance you will get how much, 6b distance from this equation, 6b, here also 6b. but from this relay line, okay, which is in excited state, okay. Now if okay, after putting j is equal to 0, then you will get 6b, which is the difference, which is the distance, first distance of this anti-Stokes as Stokes lines, okay, 6b. And now the separation successive Raman lines, this anti-Stokes, this is for Stokes, okay. Another successive Raman lines is you will get at 4b distance, hey, this side here, this side here, okay. So you will get 4b distance. Right. So we can easily here we put j is equal to 1, 2, 3, okay. So here we put j is equal to 1, 2, 3. Similarly you will get the energy, another Stokes line or anti-Stokes line, okay. So this side similarly, this is also for B, this is also for B. So here you will get at 6 VB distance when put j is equal to 0. Now okay, right, hopefully you understood, okay. I think this is all about, but I think I don't have much knowledge about this Raman Spectra, but from my side I try this much and I give you this much notes, but I don't have much idea more than that of this, okay. Some information also about this. So actually this scattering is next node point. Wave number is inversely proportional to wavelength, okay. So this side if you move this side to this side, so your wave number is increasing, means your wavelength is decreasing, okay, from this side to this side. Wavelength decreasing means your energy is increasing, okay. So that's why you are getting anti-Stokes line, okay, here anti-Stokes line, here you are getting Stokes line, because this side is energy less, you are getting less energy, this side getting your more energy, than of incident light, okay. So this relation holds for this decreasing the wave numbers. Okay, another relation means also holds scattering inversely proportional to lambda 4. Okay, so if you are keeping sample inside Raman Spectroscopy instrument and there are a lot of scattering is coming means through this sample, so that means your wavelength is, so scattering basically coming at lower wavelength. Okay, means more scattering, lower the wavelength. Okay, so basically I am trying to in this way. So as I told, this diatomic nitrogen and oxygen molecule does not do not show IR but show Raman spectroscopy. And one most important example I will give, which is very familiar to your daily life. See, nitrogen and oxygen are in the atmosphere and they are scattered the blue light. Okay, they are scattered the blue light, not the red light. Okay, because its efficiency is inversely proportional to lambda. Okay, so for red light lambda value will be high, for blue lambda value will be low. Okay, that's why the mostly scattered is happen in blue light. Okay, not red light. Okay, so sometimes if you see in sky, then you only see the blue light. Okay, which is scattered and in different way. Okay, but if the compare the cloud, cloud have very large water droplet compared to the oxygen and nitrogen. Okay, so therefore, so you just see cloud is a white in color because water droplet cannot scatter red light. Okay, so water droplet cannot scatter red light, but nitrogen oxygen scatter blue light. Okay, so that clouds see blue color. Okay, so this is informative examples. Okay, so if we write here, because writing thing always you every time you see, and if what I am talking only you will catch by listening, but writing thing you can see by your eyes and easily you will get the idea. Okay, so what I am trying to say, nitrogen, oxygen, which is present in atmosphere, they are scattered blue light. Okay, but not red light. red light is higher wavelength and blue light is lower wavelength. So for higher wavelength it require low energy, for lower wavelength is require high energy. Okay, so from sun it's coming higher energy. Okay, that's why it scattered blue light. Okay, so as I told, second example, this is example first, this is second example. Cloud है, large amount of water droplet, okay, compared to nitrogen, oxygen. Okay, so and you have many times seen the cloud, mostly you see cloud in white color. Okay, okay, so here the water droplet cannot scattered red light. Okay, here water droplet also cannot scatter red light, but it is scattered, N2 and O2, but scattered, but N2O2 is scattered blue light. Okay, hopefully you guys understood. Therefore, so that we can say cloud, see blue color. Okay, so thank you. This is I did not cover fully, but you can solve problem yourself. Okay, so hopefully you guys understood what I taught you. Okay, so thank you, bye bye. If I have any doubt, so please comment, write comment, I will